Hi guys, can you guys hear me?
Yep.
Okay, great, thank you.
Hello, Professor. Are you talking?
No, I was just waiting for 7, so everybody was here.
Okay, thank you.
Thanks, Eric. How you doing, Eric?
Good. How are you?
Not too bad, thanks. Just not, stuck at home.
Yeah.
Dude, I'm assuming JPL is also closed up.
Yes. This is the 5th week I'm working from home.
Wow.
Yeah, and there is until May 15 is the last instruction, and we don't know how long it's going to be this situation.
Yeah. Oof. Yeah.
Oh, yeah.
Can you get any work done at home? Some people are struggling with it. I know I'm struggling with a little bit.
Yeah, sometimes we have VPN connection since a lot of people using VPN connection, but other than that, I have some jobs that I'm okay. Just my daughter, if she let me to work.
Yeah.
Yeah.
Well, I guess you get to spend more time at home. I mean, that's kind of nice. Your daughter.
Yeah, I'm lucky that my wife is not working. She spend more time with my daughter than
nice.
I can work.
Yeah. So speaking of VPN, we have I guess the same problem in this class with Cadence. So let's see how this project goes without Cadence.
I'm thinking, is there any way we can connect actually access to university Cadence, university computer softwares?
I gotta ask Dr. Olson. I think the answer was no previously.
Yeah.
Just because of this particular software, I think they were kind of sensitive to it.
Yeah.
But given that we're online, but yeah, I'll ask. Good question.
Oh, it's okay. Don't worry.
Yeah. Hopefully, I think everything in this project we'll be able to do without Cadence.
Oh, okay. Good.
Okay, guys, I guess we can get started. So I hope everybody's doing good. And I don't know if it was Mark or somebody else who brought up projects last time. So be careful what you wish for, Mark. So I dumped a project on you guys. Yeah. And so anyway, but it was coming anyway. So Mark was right. It's better to have it earlier than later. So anyhow, I put up the project, and a video on Spice that I tried to make it somewhat related to the project, and also a tutorial on LT Spice, which is a particular implementation of Spice that's free, and it's works for both Mac and PC, and I like it. It's pretty, it's kind of an open platform. You can do a lot of stuff with it. And then I also put up the Spice model for our process. And I think I put up my sample circuits too in LT Spice. Okay. So anyway, so the idea behind it, let me just go through it a little bit. What we're doing is, and again, because we don't have access to Cadence from, off campus, I tried to basically do it an all Spice project, so you guys could work from it from home. So the idea, the end idea here, the end goal of this activity is to compare the delay. Basically, it's this graph is the end goal. So you're comparing the hand calculated delay as a function of fan out to the delay you calculate by hand using our logical effort activities. And you plot them versus, H is the fan out and the vertical axis is the delay. So this was just an example of an inverter I did. But the idea is this is the logical effort curve for the gate you were assigned for project one. So if that gate was like a NOR 3 with a certain specific values for the widths, etc., then like that's what you would end up using, and see how basically hopefully it gives you an idea about logical effort. Okay, so the way you start is the first several steps. I mean, the first step was, just kind of get yourself familiar with LT Spice. If you want to use, by the way, if you guys want to use, P-Spice or any other kind of Spice, you're welcome to do it. You just have to grab that text file I send up for the model file and, feed that into your Spice simulator, whatever it is. And because, the output is just, graphs and stuff and numbers to me. So I don't really need to, get your database or anything. But, if you use LT Spice, if there's a problem, it'd be easier for me to help you guys debug it. But I'll leave it up to you guys. Whatever, that's one nice thing about Spice is there's a bunch of different programs to run it. Okay, so the first few steps, so 2 through I think 4, but let's look through it, are to just get the parameters you need to come up with your logical effort. So you remember the parameters we used for coming up with the hand delay model calculation was the resistance VN, the equivalent resistance, and the equivalent resistance of the P, the gate capacitances, and the drain capacitances. The drain and the source capacitances, say, but mostly the drain capacitances, okay? So basically, the sort of step 2 is to find the effective gate capacitances. So for step 2, you don't use your own gate. You actually use inverters with the size ratios I've put in there, because you're just trying to get the gate capacitance. It doesn't matter. I guess you could use it with the logic gates you guys have. It'd just be sort of complicating your life. So just use the inverters. And the idea is that sort of the first 2 stages, the first 2 inverter stages, are to shape the input. So that's these X1 and X2, X3, X6, X4, X5. Those X's are just the name of those inverters. It doesn't mean they're like you know, ×2 strength inverter. The strengths of the devices are written above and below. So the first inverter is, you know, sort of minimum size NMOS, twice minimum size PMOS. Second one is four times minimum, et cetera. So we're sort of scaling up the sizes of those inverters. And then the X4 and X5 are just loading for X3, okay? And so what we've done is we've made X3 and X6 are in parallel, so they get exactly the same input. And then X3 is driving this gate, which is 32, is driving X4, okay? And X6 is driving a perfect capacitor. So if you do transient stems, rise and fall times, and or you know, prop delays, say whatever, whichever one you want to do, and you basically get the waveform on node G to line up on top of the waveform on node D. That means the C delay, or perfect capacitor that you're adjusting up and down to make the voltage on gate G match the voltage on D. You've made that C delay be the same as the input gate capacitance of X4. Then you know the size of that total input gate, which is, you know, the size of it 32 times minimum NMOS and 64 times minimum PMOS in parallel. So you know what you're driving. And so you can get basically the capacitance in terms of femtofarads per micron of transistor width for this 180 nanometer process. Okay, so step 2, you're just doing that. You're coming up with C sub G. And then, oh, sorry, for this, you want to make sure that you set the area of drain, area of source for your transistors to 0, because you don't want the drain capacitance of X3 and X6 to affect your calculations. Theoretically, it shouldn't, but you want to sort of get rid of them. It's because you just want to see the gate capacitance hanging off of that node. Okay, so make sure that's zeroed out. Okay, number 3 is now you want to get the drain capacitance, and what you do is something similar. X1 and X2 are just generating the appropriate input waveform, appropriate rise fall times, and going to X4 and X3 in parallel, so they both get the same input. And then you've got a NMOS transistor, M1, that's off. So you've hooked up the gate to ground and the source to ground. And now you've actually put in the calculated, and you have to be a little careful here, make sure you calculate it, area of drain, perimeter of drain correctly. Plug it in there. By the way, I would suggest you use the M1 bigger than minimum, just because, you know, I think it's basically will allow you, you know, as you do the sims, you'll see, like, you'll get, if you use a minimum size drain, you'll get a very sharp transition on node D and also on node E. So it's a little harder to eyeball where the lines are, whether they're really sitting on top of each other or not. So I'd use a relatively large M1. Anyway, so you're doing the same thing, and so this would calculate the, this would get you the, if you move C delay up and down, or increase or decrease to line it up with E with node D, you know, the capacitance per unit width for M1 for the drain capacitance, okay, which is the other thing we need. And then you can do the same thing for a PMOS. So you drive on node D, instead of that N transistor, you put a PMOS with the gate hooked up to supply to turn it off and only see the drain of the PMOS. Oops. So you have those two now. Then what's left is the effective resistance. And basically you do that by using the sort of a 2, you know, minimum size inverter driving let's see cursor here. Nope. Okay, so use a minimum size inverter driving at different fan outs. Okay, so if you look at this equation in West and Harris, section 8.4.5, you can see that if you use two different values, you can basically do a differential measurement. You can use two different values for fan out, so two different H values, and that way you can only end up with this difference in prop delay for rise and fall times. And so you can just measure that off your SPICE simulations, and the gate capacitance, which you've got from exercise 2, and then you can calculate R sub n and R sub p. Okay, so then you have everything you need for your hand calculations. Okay, let's see what I want to say about this. So I think this was the part that confused most. I think most people got confused. This was similar to a project we'd done last semester. And I think what confused people was one, for problems or steps 2 through 4, they were using their own gate, their assigned gate. And I would suggest against that, that's gonna complicate things. I would just use inverters of the size suggested in this example, just to make it easier for yourself. So I think that was the major thing. The second thing was make sure when you're driving your inputs, some of the gates are very, very slow. Like if you ended up, I don't know, you ended up with a 3 input or 4 input NOR gate or something, it's very slow. So make sure you're getting a full transition on the outputs from low to high and high to low. So especially in 0.5, which is now what you do, which is the setup you have for your own gates. So this would be an example if you had a 2-input NAND gate assigned to you. And again, you have the first 2 stages, X1 and X2, are to basically create a reasonable input into your device that you're testing, which is X3, X4, and X5 are loads, and H is the fan out. Okay, so you do H1, H2, H3, and resim this with different M factors. And I talked in that in the SPICE tutorial, LT SPICE 1, about how to set up your M factor. So it's a parameter that you can easily set to make the simulation sort of go a little bit faster. And again, here, just make sure you get good full supply transition, so 0 to 1.8 and 1.8 to 0 in each one of these A, B, C, D, E, and F nodes. I think that sort of confused people. So again, for some of the gates, you're going to end up, they're going to be very slow. So you're going to have to make your pulse widths long enough for everything to settle. And then because this method only uses one input, so in this case, you're using one input of the NAND gate, you have to tie the other inputs of your logic gate so that they don't affect basically you're trying to emulate an inverter using your gate. So in the case of a NAND gate, you just hook up one of the inputs to a high value, or you would hook up all the inputs to a high value if you had a multiple, like a 3 or 4 input NAND gate. Okay, so you'd measure the delays there, and you'd plot that into something like the simulated, which will be the blue. So you do this for H1, 2, 3, and 4, and using the values of Rn, Rp, the gate N and gate P should be the same number, and then CD and CDP are a little bit different. So use those to hand calculate your logical effort for your gate, and that'll be something else. In this case, it would end up being the orange curve, and plot those two, and they won't be exactly the same because, you know, there's like 3 or 4 things that are assumed in the logical, hand calculated logical effort. I think the primary one that's the difference between these two is the hand calculated logical effort is assuming a very fast rise fall times, whereas here, because we are shaping, we're shaping the inputs and we're also we're basically shaping the inputs, we get a more reasonable rise time, so a slower rise time, which gives the device a higher delay than hand calculated. So that's the major effect. Anyway, so that's the project. Any questions on the project, or I don't know if you had any questions on the SPICE video or anything like that. Anyway, you're always welcome to send me emails as you guys get started. So let's see. Okay, so let's get on our next topic. So I'm gonna, I think we spent enough time on logical effort. I think we had like two sessions on logical effort. So I think I covered everything I wanted to do there. And so I'm moving to our next section, which is interconnects. So, you know, so far we've been mostly talking about transistors, but a big part of VLSI design are the wires that are the interconnections between those transistors. And they're actually, you know, a very important part of the performance of the device. So, you know, on the left here, we've got, you know, what wires look like in a schematic, just look like lines, but physically they're made out of some kind of metal. They have a certain width. Boy, did I post these? I may not have posted these yet. Did I post them? I don't remember. Do you guys want me to post them real quick before I keep going, or?
Yeah, can you post it for us, Professor?
Sure, let me just do that real quick. Sorry, guys. Let me see. Sorry about that. Let's get this guy. And every time I try to do something real time, it's like incredibly slow. Okay, here we go. Spring course documents. Okay, guys, hopefully it's up there now. Might take you guys a while to see it. Sorry about that. So let me just keep going as that thing is uploading, hopefully. Let me just double check, make sure it didn't. Yep. Okay. So anyway, these are like the actual connections or sort of real metal lines. They have certain width, they have certain thickness. they have a certain separation from each other, and they have a certain resistance. So, and that's, affects our performance quite a bit, okay? And the reason is most of what the chips are made out of are actually wires. So you have, you can see a lot of transistors, but they're sort of buried underneath a ton of connectivity. And it makes sense because you can just think about all the connections you could have across your chip locally, fan outs, fan ins. You need to route power, ground, clocks. So basically have a ton of wires sitting on top of your transistors, okay? And they have significant effects on speed, power, and noise, maybe as much as the transistor, sometimes more, okay? So here's like an example of what things look like. So here's a 90 nanometer process and a 45 nanometer process. And just looking at the 45 nanometer, you see the transistors are these little itty bitty things down here. And this whole stack here is the interconnection stack. In this particular case, it has 8 metal layers. You see that the sort of layers, the metal layers down, I don't know, these first 4 are about, oh, and then another interesting thing, as these processes get tighter and tighter, you see the aspect ratio, which is the ratio of width to height of these devices. So this would be the ratio of sort of the height to width. So these things are getting, the aspect ratio is getting bigger and bigger as you are going into smaller and smaller processes. So these aren't squat wires sitting next to each other. They're more like, they look like more like that. Okay, and so these are sort of the same size, thickness, these first few metal layers, and then as you get to large, further away from your transistors, they tend to get thicker, and the minimum feature sizes tend to be larger, and you end up using these for power and ground, etc. Okay, so anyway, this picture I think says a lot about what an important thing like interconnects are, about how much they overwhelm physically your transistors. Okay, and each one of these pieces of metal that we're calling interconnect has resistance, capacitance, will have crosstalk, etc. Whoops, come on, let's go. What's going on here? Oh, the slide doesn't want to do anything. Okay, so if we look at the models for a wire, so wires have, resistance, they'll have some inductance and some capacitance, okay? And then there is capacitance between wires, and there's different inductances in different places, etc. But when you look at wires inside the chip, for the most part, wires inside the chip, you just have to worry about resistances and capacitances. The inductances inside the chip are not big enough to worry about for most lengths and speeds, most lengths and speeds, okay? So basically you end up with these wires that have, if you just look at the capacitance, you'll have a capacitance to ground, which is, the substrate or the power supply or the ground, and then they have a capacitance to other wires around, okay? And so, and then, these parasitic values, or these parasitic capacitances, or, affect both the noise performance and power consumption and speed. Okay, so here's a sort of a distribution of the type of interconnects we'll have on a chip. So this horizontal axis, as you see, is the length of the interconnect. Okay, and it's a log scale. So this is 100 micron, a millimeter, 10 millimeters, 100 millimeters. And this is the number of interconnects that have that length. And basically what you see is there is significantly fewer, regardless of what generation device, these are all Intel devices, Intel processors. Regardless, there's very few interconnects that are long. So these are very long interconnects, clocks and those kind of things. There's relatively very few of them, and most interconnects are, 10 to 100 microns. So, or, this is sort of how the flow of the size of interconnects. So you have interconnects that are, are going across the chip, but there's a few of them, usually, probably talking about clocks are a good example. And another example may be, buses that are running across the whole chip. But most of the interconnects are within individual blocks or individual sets of gates, okay, unfortunately. Okay, so when we talk about the capacitance of interconnects, when you drive a gate, so this is one inverter driving another inverter, okay? And, we've talked about all these different capacitances, the drain capacitance of the P, drain capacitance of the N, the gate capacitance of the next stage of driving, but then you'll also have this interconnection capacitance, okay, that loads down your circuit in parallel with the devices that you have, other devices. So basically, when you're looking at your load capacitance, you lump them all typically in one load capacitance, which is the interconnect capacitance plus whatever is the gate capacitance of the stage you're driving times, the fan out, let's call it the H. Okay, so the wires, they're like, there's two big important factors for wires or interconnects. One of them is the type of metal that's used. Whether it's aluminum, copper, or the most popular, I would say. And so that's one, and that gives you a certain resistivity. And the other factor is the geometry. So, you have what's called the pitch, which is important. So most of the geometric factors are decided by how you do layout. So, you could say the minimum width of a line and the minimum space of a line, those are defined by the design rules. But what most people care about is the pitch, because that tells you how close you can, basically how, if you have a certain width, area width, how many wires can you run through that? And for that, you need both the minimum width and the space between the wires. So basically, you'll hear a lot about wire pitch, which includes both of those factors. And the aspect ratio is the ratio of the thickness to the width, which I talked about last time. I mean, just a couple of slides ago. And in older processes, we're used to, if you look at a cross-section of the wire, mentally always think about wires having this kind of aspect ratio, something less than 1, but really in reality, modern processes, it's more like something like this, thickness and the width. Okay, and this has, the reason they do that is because they want to pack a bunch of these guys next to each other. but you also need a minimum resistance, so that's why they had it to make them a minimum thickness. So you end up with this high aspect ratio. But this has a important effect in that if you notice, you could get a lot of crosstalk because you have a lot of area between the wires that are running next to each other. I know we'll look at that. Okay, so the layer stacks, older processes had fewer metal layers. So this is a 0.6 micron process, only had 3 metal layers. And, typically people, by the way, tend to give sort of an orderly layout. They tend to lay out, metal lines in different layers that are adjacent to each other orthogonally. So let's say if you run your metal 2 lines vertically, you tend to route your metal 3 horizontally, so you'll kind of always have escape routing. You'll always be able to make connections, okay? So anyway, you'd have something like 3 layers, but now you really have, a lot of metal layers, because it ends up that a big part of your problem in modern processes is the connectivity. You have so many transistors in your chip that you need a lot of metal layers to connect them. They tend to be very narrow. So let's say for a 65 nanometer process, say for a lambda of, was it like 25 nanometers? So, the width of a metal line might be, 125, 150 nanometer or something like that. So they tend to be very narrow, especially the metal 1. Metal 2, as we saw, they're about the same thickness, but they're getting, as you go from, say, metal 2 to metal, I don't know, 5, 4 or 5, whatever it is. They tend to be slightly thicker and wider, but about the same, I would say, as each other. And then finally, as we saw, the really top metal layers are sort of saved for sort of coarse layout structures like power, like ground, like clock. Coarse meaning that, basically you can put a swath of a whole wide power metal sort of rectangle and have all your circuits tapping off of it. And same with the ground, same with the clock. And all these things are running across the chip and need to be very low resistance. Okay, so that's why they save the thickest top layers for those typically. You don't really use those for routing. You could, but you have very coarse routing. And this is like a simplified model of, sort of a mental picture of what the interconnects look like. So this is sort of a water pipe model where you have a resistance sets a limit to how much current you can flow across it. The capacitance is how much you have to fill this sort of reservoir before the real signal or the real current goes through. And inductance is this thing that the faster your current goes, the more it's fighting it. So it's affecting your flow rate. Okay, so now here's what something like a bit of magic that goes back to our RC type simplifications. Okay, so if you take, what we said is we're going to use we're just going to have resistance and capacitances for our interconnect layer. So we're going to ignore basically inductance for most of the frequencies that we're doing. So let's say you have an R and a C. And let's say it's a very long interconnect. Okay, and so you have a lot of R and a lot of C, and let's say this is, I don't know, let's say it's a millimeter, so for the sake of discussion, which is pretty long in sort of chip space. So if you just, let's say, calculate the resistance or the series resistance of the line, and calculate the capacitance of the line and treat them as just one resistor and one capacitor, you're actually going to get a pretty pessimistic RC delay for the line. That would be sort of a pretty pessimistic number. Because in reality, this looks like a distributed line. So basically, you can look at each little segment having its own resistance and capacitance. So that's, a more realistic model of what's happening. In fact, sort of if you look at, the real system is, sort of each infinitesimally small section has an R and a C. Okay, so that gives you a more realistic model of what the RC delay of that line would be, except it's a lot of components, depending on, you need a lot of segments to get to a realistic number, okay? And this is kind of a magic that you can use what's called a pi model, and just with using 3 segments of a pi model, you can get very close to your actual simulation value. So let's say you had let me make life easy for myself. Let's say you had a 3K ohm. Is that right? Yeah, let's say you had a 3K ohm and you had a 600 femtofarad. That was the total value. So that was the total resistance and capacitance of the line. So that's what you had. If you model this as, so a pi model would be 100 femto and 1 kilo, 100 femto. So that's 1 pi. Here's another pi. Oops. Sorry, that should be 1 kilo. 100 femto. And the final one, 1 kilo and 100 femto. Then you connect these 3 components up. Just these, so these are 3 of these pi models. Okay, hooked up. So 3 segment pi models. Gives you a very, very accurate result, very close to, basically if you were using this sort of segmented model, you would need 100 of these segments to be the same accuracy as sort of these 3 pi. So there's some magic with this pi model, but honestly, I don't know why it's that accurate, but anyway, it is. So that's what the model you want to use is this pi model, and you want to divide up your resistances and capacitances and connect them up together with 3 sections, and then you get a fairly effective hand calculated model of your interconnect. And let's say you were going to basically look at the delay here. You would have, let's say you have an inverter driving this point. So it has let's say it's looking at driving a 0 across this. You'd have the delay of your pull down network from that inverter, your R sub n, okay, on one side. And then you would have your load. So this would be the C sub G of whatever gate you're driving. Okay. And then you can use the same sort of Elmore delay technique that you used with the gates. So the delay would be, R sub n times 100 femto plus R sub n plus 1K ohm times 100 femto plus R sub n plus, no, sorry, this is 200 femto because these 2 are in parallel. So we'd have to add those, plus R sub n plus 1 k ohm plus 1 k ohm times, again, 200 femto plus, and you get the idea. So basically use the same Elmore delay concept and these pi models to get a pretty accurate hand calculation of your interconnect delay. Okay, so that's kind of the model you use, okay? And so we talked about the geometry being important of the interconnect. And then the second factor that's very important is the resistivity of the interconnect, or basically, you know, the wire. So the first element is the wire resistance, okay? So the resistance is made out of this resistivity, which is dependent on the type of material. So here's the resistivity of different materials. So this has nothing to do with VLSI. So when you look at this micro ohm times centimeter, you're saying if I had a cube that was a centimeter by a centimeter by a centimeter, and I connected this side and the sort of back side, what would be the resistance from this end to that end? And so this is the bulk resistivity. So it'd be like if you had a centimeter cube size of copper, it would have 1.7 micro ohm of resistance from one side to the other. Okay, and you notice that, so that, as I mentioned, I think that these are all sort of popular types of interconnects, but the most popular ones were, you know, aluminum was the one people used a lot, sort of in older processes, and things have moved to copper because the resistance is significantly lower than the the resistivity is significantly lower than resistivity of aluminum. Aluminum was nice because you could just lay it down, if it wouldn't out diffuse, whereas copper tends to diffuse into silicon and cause problems. So there's processing issues with copper that also affects its performance. So you need to surround it by a diffusion barrier. But anyway, copper, because of the lower resistivity, it wins basically. So most of the processes say at, you know, things start at maybe 90 nanometers, I would say, 90, yeah. I would say 90 nanometer and below, it's pretty much, and below is pretty much all copper. The interconnects are all copper. Everything except usually the very top interconnect is aluminum. So you can wire bond to it because, you know, copper isn't a very friendly metal to wire bond to. But anyway, you just basically have to call it copper interconnects. Okay, so the total resistance of the line is this resistivity, this bulk resistivity, times the length over width over the thickness of this block. Okay, so now we're talking about a chip. The lines have a certain length. So the longer the line is, the higher the resistance. The wider it is, the lower resistance, and the thicker it is, the lower the resistance. Okay, so this is just like a very basic equation of geometry and resistivity of the material giving you the resistance of the line. And it turns out that, you know, because we're talking about, so sorry, let me, before I say that. So, you know, a lot of special units in chip design are made to make sort of design easy, let's say. So one of the factors you'll see here is we've got, you know, you can draw, when you do a layout, you can draw the length and width of the line yourself, but you have no control over the thickness of the line. That just comes with the process. The foundry said the thickness of metal one is whatever it is, you know, it's 300 nanometers or whatever. And so you cannot modify it. So what you can do is you can basically combine the rho and the t, and this is r sub w, and basically then all you have to worry about, and then this basically this, all you have to worry about is this length and width. Okay, so basically you end up with this thing called sheet resistance, okay, which is what's ohm, and this is like, gets very confusing, but I think you have to do some amount of layout and some amount of extraction to see the usefulness of this unit. So if you look at, for example, process parameters, they'll tell you the sheet resistance of metal 1, metal 2, etc. They won't tell you the resistivity of metal 1, metal 2. Rho is the resistivity. Sorry. So it'd be this guy. So if you look at it, so now all you have to do is to figure out the ratio between length and width, and you have this basically this sheet resistance to come up with the resistance of the line. So all, if you have something that's 2L long and 2W wide, so 2L over 2W. Okay, so this guy, the ratio is L over W, and this guy is L over W also. So these two lines from end to end will have the same resistance. Okay, so you don't need to worry about this thickness or the resistivity. All you need to do is to count this ratio of L over W, known as the number of squares. And you can multiply that by your sheet resistivity, and you got the resistance of the line. Again, it just looks overly confusing right now, I think. But again, because you have no control over thickness, and with just having a single element, which is this new thing we made up called sheet resistance, you can just look at your layout, look at the ratio of length to width of what you've drawn, and multiply by this to get the resistance and get the T, the thickness out of it. Okay, so you'll see this in your process rules, etc. Okay, sheet resistance. So that's the resistance of the line. Okay, then there's also the contact resistance. I think while you guys were doing your project 1, I was talking to some of you and suggesting that you want to put as many contacts as you can. Instead of, you could have just connected these two metal lines. This is metal 2, say, and this is metal 1, metal 2, metal 1. Theoretically, it could have just used a single contact instead of 8 to connect these two. But contacts, vias, these things all actually have a relatively large resistance, okay? So these resistivities that, talking about these sheet resistances, are in the milliohms range that we're talking about. But here you can see a single via might have 20 ohms of resistance, which is gigantic when you're, let's say you're using it in a power supply or even an interconnect. And if you're dropping multiple vias up and down, you can end up with a lot of resistance. But if you have the area, you can drop in, and that's why you tend to drop in as many as you can, and cover, given the minimum pitch of your vias and contacts, to lower this resistance. And also, besides the lower resistance, this also gives you higher reliability, because if one of these vias fails, you have all his neighbors that can still supply the current. So you won't have a broken chip. You will have a slightly higher resistance in this line. So anyway, contact resistance is a very important thing. Okay, so I talked a little bit about copper having lower resistance, okay, but the problem is it tends to out diffuse into silicon. So what they have to do is to surround the copper with a low resistance diffusion barrier, okay, which has higher resistance than copper. So it means that you don't get this full T times W of the copper is not giving you the low resistance, but you have to subtract out the width of the barrier. And then also because of the processing, I'm not going to get into the processing much, but they have to polish the copper. That's how they get rid of the copper they don't need. That tends to do this thing called dishing, or eating into the top of the copper, and again, it's making it sort of a smaller cross section. Okay. So anyway, you don't need to remember this equation. You just need to know that you have this problem with copper. So you're using copper to reduce the line resistance. It's very effective, but it's not as effective as it could be, or as effective as the resistivity numbers imply, because of these factors, these complications in processing. So that's sort of the takeaway about copper. Okay, so let's look at this example. Okay, so so this should be micron, I think. Okay, copper wire, resistivity of the thin film. This looks like it's completely gone. It comes down. This looks like it's completely mangled. Let me skip this and I'll work this out for you guys offline. I think the problem got totally mangled when I copied it over. Times 10 to the 8. Yeah. Sorry guys. So anyway, I'm gonna leave this for, maybe I'll put it in the homework or part of the examples. Okay, so all in all, when it comes to the resistance of the lines, these are the options you have. Okay, you can go to a basically, as you go smaller in technology, your line resistances actually go up because everything's getting thinner. So basically, people are careful about what they scale. So when you go, say, to a 45 nanometer process, not everything, not all the metal lines are going to be 45 nanometer. They're kind of selective about which ones they'll scale down and which one they won't, to basically give you a lower resistance for some of the thicker lines. Okay, you can use copper, and you can try to place the parts that are interconnected as close to each other as possible to just reduce the wire length. Okay, and more interconnection layers mean that you can reduce the wire lengths, because if you had fewer interconnect layers to be able to do that routing, would take more space. You would have to just separate your transistors unnecessarily, and that would sort of stretch out your connections. Okay, so more interconnection layers means shorter wire lengths. So if you're a designer, you just want as many interconnect layers as you can. The problem is the fab charges you extra for each metal layer you use. So typically, let's say you had a process that's capable of having 10 metal layers. You have the option to run typically anywhere between, say, 6 and 10 metal layers. And if cost is of the essence, the per wafer cost, you sort of try to get your design into those 6 metal layers But if performance is more important or you just have no option, you'll go to the 10 metal layers. So then anyway, as a designer, the more metal layers you have, the easier your work. So that's what you like. But you know, the product managers and those guys makes the cost of the part go up. So there's some negotiation there about how many interconnect layers you can use, even for a particular process. Okay, another factor in the resistance is just the resistance of the polysilicon on the gates. So let's say you have this is your transistor, this is your poly, say, and it's got this connection. Okay, and let's say you've got a metal 2 line coming from, you know, God knows where. Metal 1, sorry. And so this has a certain resistance, but then so does this. Your gate itself has a certain resistance, and because typically polysilicon, it's a polycrystalline structure, it's a semiconductor, it's going to have much higher resistance per unit, per square, let's say, than a metal line. So this your gate resistance ends up being a pretty big factor, especially if you're driving, you know, if you're looking at output drivers, you end up with some really wide transistors. Your transistors may be, I don't know, 500 microns wide to get a lot of current on your outputs. So that could be a lot of resistance. So people, what they do is to reduce your polysilicon resistance, they sort of put this thing called a silicide, which is, you know, a combination of different metals and silicon on top of your polysilicon to reduce the resistance of the poly. Okay, and so, you know, depending on the type of materials the type of metals you have, depends on the process. But basically, if you have silicide, it's a lower resistance polygate. But again, it's another layer and it costs you more. So it depends on whether you need it or not. Okay. And, you know, we talked about the different metal layers for interconnect. If you get desperate, and I really mean desperate, you can try to use like just polysilicon as routing. Say if you're, you know, you guys saw when we had a PMOSFET and NMOS in our projects, we could, you know, connect it to the 2 gates with just a poly. Okay, let's say we'd used all the metal lines, we needed them for other interconnections. But so for very, very short distances, you can use poly, but you can see how high the sheet resistance is compared to using aluminum, which is already higher than copper. So, you know, if you get desperate, run out of routing availability, you can use polysilicon. Again, polysilicon with silicide is quite a bit better, okay, but it's still much higher than aluminum. And, you know, you can even use diffusions, but diffusions tend to have a lot of capacitance, and the resistance is voltage dependent because they're, you know, diodes and have depletion regions. So you got to be careful about that. So anyway, if you get really desperate, you can use poly or diffusion to route very locally, but be very, very, very careful about that. When I first went to JPL, this is back, you know, when I just graduated out of grad school, they were troubleshooting this chip that had come back, this image sensor chip, and wasn't working. And in the end, we discovered, not we, I guess the person who designed it, discovered that the decoder lines were all drawn with poly, which looked like a very efficient layout because they're all, the decoders are all lined up next to each other, and all you have to do is to run a long polyline, and it creates the gates and the connections between the gates all in one shot. Looks like a real efficient layout, but that higher resistance value made those decoder lines have a very high, sort of very large RC delay and very long rise time, fall time, and the chip didn't work basically. So anyway, you want to be really judicious about using these other layers for interconnection. Okay, so that was all about resistance, the options you have, and why you have those options. Okay, so that's the R. The second thing we have is the C, the capacitance of the lines. Okay, so when we look at a parallel plate capacitor, let's say if we look at our metal lines as a parallel plate capacitor. Okay, so let's say this is the metal line, and let's say we're looking at the capacitance to the substrate. Okay, if you have a parallel plate capacitance, you worry about the width times length, give you the area of this parallel plate. So this is the area. And so the capacitance is the dielectric sort of constant of the material you're using over the thickness of the dielectric times the area. Okay, that's what would happen if you had the parallel plate capacitor, which is, a lot of times we look at sort of a simplified version of looking at capacitance. Okay, so this would be your equation. Now the problem is, because of this large aspect ratio of interconnects, and because you have a lot of them that are narrow, you don't just have a parallel plate capacitance when you lay it down. So what happens is you have the parallel plate capacitance, but because this thickness is so large compared to this width, and because these lines are very narrow, you end up with a huge amount of fringing capacitance, okay, which is caused by the electric field lines that are terminating from the edges of the metal lines to the substrate, okay? So that's actually a very big part of the capacitance, as we'll see, depending on which wire we're talking about, which process, etc. So the total capacitance ends up being the parallel plate capacitance plus the fringe capacitance. And one way to people model it, again, you don't have to worry about this equation, but the way people model it is a combination of only a parallel plate capacitance, and then they model these edges as sort of two halves of a circle and calculate the fringe capacitance from there and sum the two up to get the total capacitance. But anyway, the fringe capacitance can be the dominant capacitance in a lot of processes and geometries, okay? And the other thing is when you have a complex layout structure, okay, so this is just a metal plate, sort of this is like two plates talking to each other only. In reality, there's a lot of layers talking to each other or have capacitance with respect to each other. So this is a cross-sectional drawing. So imagine you have a very long metal line that's going into the page, okay? So we're looking at its cross-section. So that's this guy, okay? It might have, so that let's say this is in metal 2 for the sake of discussion. It might have another layer stuff running underneath it in metal 1. It'll have stuff running over it in metal 3, okay? So it'll have a certain capacitance to the metal 1 layers running underneath, certain capacitance to the metal 3 layers. And then, because it's relatively thick, and it'll probably have other metal 2-layer lines, signals. This is, let's say, signal 1, signal 2, signal 3 in a bus, say, for the sake of discussion. You'll have other metal lines running in parallel to it in the same layer, in metal 2 in this case, and you'll have capacitances to those as well. So you'd have to worry about the capacitance to the neighbors and above and below. Okay, and these all sort of talk to each other depending on how close these are. Like, you know, you would have, if these are close, you have a large capacitance, but then they might terminate some of the fringe capacitance that goes to here. That would terminate here instead of going here. So there's some complications, but you just kind of assume that you can add all of these in sort of in a linear way to each other as if the other ones don't exist for simple calculations. Okay, so again, you don't have to worry about this equation. All right, what you get in typical process documentation is you get a table like this, okay, that gives you the capacitances. So let's say you're looking at let's say the capacitance of say you're looking at the capacitance of poly to metal 1. Okay, so it would be here. There's usually more, I'm sorry, I sort of cut and pasted it. There should be sort of a legend here about what we're talking about. But this red is capacitance of poly to say, this is AL1, metal 1 here, okay? This top value, again, so it'll tell you in the table, is the parallel plate capacitance. So and it's given in units per micron squared. So in this case, it'd be 57 femtofarads probably per micron squared, okay? And this bottom value is your fringe capacitance. And this is given in femtofarads per micron. So in this case, it'd be 54, or, you know, it could be anything. It could be attofarads or, you know, whatever. I'm just saying. In fact, sorry, it is probably attofarads. That would be too high. So this is probably attofarads. But you get the idea. So the fringe capacitance is given per micron of length. Okay. And the parallel plate capacitance is given in microns squared, because whether you have a wide line running or a narrow line running, these two will have the same fringe capacitance. Because they have, you know, they both have two sides that have the same, as long as they are the same length. Well, it's not, doesn't, per unit micron of length, they'll have the same fringe capacitance. So there you look at it as per micron of length, okay? But they could have significantly different parallel plate capacitances because one line is much wider than the other one. So again, remember the parallel plate capacitance is per micron squared, and the fringe capacitance is per micron of length, okay? And you have to basically add those two, and you get the value of capacitance, say in this case between a poly and aluminum line that you have. Okay, so we got 6 minutes left. So, you know, just as there are trends in the resistances of lines, there's trends in capacitance. I think the biggest trend in the capacitance is using so-called low K So this is sort of mentioned a lot, low-K dielectrics, which is, things that have dielectric constants lower than silicon dioxide to reduce capacitance. And sometimes they use air pockets, again, to reduce this dielectric constant for your capacitance. I think that's the biggest factor. And, the rest of it is kind of driven by the aspect ratio of your lines, the width of the lines, and how long they are. Okay, so the other factors, so these are all sort of the typical metal lines. If you have, again, diffusions and polysilicon lines also have their own capacitances. The diffusion capacitance can be very high because, again, if you have, let's say you're using silicon, let's say you're using a diffusion, so let's say you're using an N plus to, so this has, if I look at this cross section, it's N plus to P. So you have this junction all around. That's giving you a very large capacitance. So if you're running lines with diffusion capacitances, they'll have very high, this should be, I think this is per micron, very large capacitances, about the same as gates. And so we do not want to run lines with diffusion as much as you can. The other thing I mentioned is because this capacitance, this depletion capacitance is dependent on the reverse bias voltage. The capacitance is also voltage dependent. So definitely if you have like analog signals or something, you definitely do not want to run those in diffusion under any circumstances. And they also have high resistance, as we saw. So again, try to avoid those. Also poly, it's not quite as bad as diffusion, but it has a very high resistance. So again, try to avoid using these for interconnects as much as you can, and only use them as exceptions, and make sure you study each exception and manage it. Okay, so this is an example of a, wow. These things got totally angled kilowatt. Gotta fix these. But anyway, I think I'll put this in your homework so you can solve it again. I apologize. I think a lot of these numbers and equations got mangled using these examples. Okay. And then we talked about using Elmore delay. I think we already talked about these. Basically use the same techniques used for the gates. So for example, this Elmore delay would be, R1, C1 plus R1 plus R2, C2 plus R1 plus R2 plus R3, C3, whereas the delay to this point would just be R4, C4, the RC delay. Okay, so use the same technique of Elmore delay. Okay, so I think this is a good place for us to stop, which is another important topic. So that was the parasitics, the RC parasitics, and we've talked about how they just affect the speed of the connections. But another thing that happens is you get crosstalk between lines, which is a pretty important effect. So we'll pick that up in our next lecture. Hey guys, any questions? If not, thanks a lot, guys, and have a good evening.
Thank you. You too.
Thanks.
Thank you. You too.
Thanks.
Take care, Professor.
Thank you.